Good day everyone and welcome to our video on steel design featuring flexural members. All right. We'll be discussing for today the overview of flexural members and what causes the failure of such members. And we will also be considering some formulas that are provided for us based on AISC ASD, allowable stress design, and as well the provisions or specifications that are also being used in our NSCP 2001. All right, let's have a quick overview over flexural members. So basically, these are beams. Now we're familiar with beams. Beams are defined as members acted upon primarily by transverse loading, often gravity, dead, or live load effects. And there are many different types of flexural members in a structure. We have girders, we have joists, we have purlins, girts, and lintels. All right, so we have this definition over here. Girders are the most important beams. These are the very big beams that we see in structures, which are frequently at wide spacing. Joists. Joists are usually less important beams which are closely spaced, frequently with truss-type webs. Purlins are roof beams. We're familiar with this. We look at how roofs are being constructed or built. So purlins are roof beams spanning between trusses. Stringers are longitudinal bridge beams spanning between floor beams. And girts are horizontal wall beams serving primarily to resist or principally to resist bending due to wind on the side of an industrial building, frequently supporting corrugated sidings, usually warehouses or other industrial buildings. Lintels. These are small beams placed on top of windows or on top of wall openings. All right, including doors. Okay, let's proceed now to what happens when we have a flexural member that is being subjected to different forms of loading. Okay, so we can see here on our slide, we could see here the mechanism that's involved. If you're going to zoom in over this first part over here, if we, for example, load our structure with a concentrated load, there would be what we call lateral torsional bending. So as the beam carries over this load, okay, the middle part of that would sway on its side. And if this is the original position of the beam, it will twist on its side. And that twisting effect is called lateral torsional bending. All right. Now, to prevent that from happening or to minimize the effect of the weakening effect of lateral torsional bending on our structures, we apply lateral supports. And usually the lateral supports are placed on the compression flange of our structure, of our building, of our beam, so that compression buckling of this compression flange is hereby limited. Okay. Or if it's not attached onto the compression flange, sometimes we use cross frames, all right, which directly connects the flanges of our beams between adjacent beams to prevent this torsional buckling from happening. Or sometimes a diaphragm is being used. A diaphragm, which is a plate that connects them at specific portions. So cross frames, bracing of the compression flange, or diaphragms are hereby denoted or known as lateral supports. Sometimes we also use support bracings. It could be a truss itself. A truss could be used as a support bracing, and this could prevent this from happening, all right, or to minimize the effect of lateral torsional buckling for our beams. Okay, so let's now proceed with the bending. So if this is our beam, this is the strong axis, and this is the weak axis. All right. Okay. Now, if the bending is like this, all right, if this is the bending, that's how it is bent. This is bending about the weak axis. Okay. So it's being bent about an axis that is proportional to the web. If the bending is like this, This is bending about the strong axis. Notice the difference in the two. Okay? The orientation of the bending. Now, beams are most usually designed or positioned or oriented in a way that strong axis bending happens. Because with strong axis bending, we're utilizing the maximum capacity of our section. That is why in sections, most sections, the Ix or the moment of inertia with respect to the x-axis is greater than the Iy. And that means that the x-axis is the strong axis. And therefore, we will have bending about such strong axis. Okay? Now, before we proceed with the procedure that we're going to go through in determining the allowable flexural or bending stresses of beams, especially the provisions found in NSCP 2001, we take note of the following parts of our section, the properties of our section. Of course, we have the depth, that's D. Okay. TF is the thickness of the compression flange. TW is the thickness of the web. B is the depth of our section. BF is the base of the compression flange, or also the width of the compression flange for the other flanges. All right, AF is the area of the compression flange, which is just simply BF times TF. We could simplify that as BF times the TF. And then FY is the yield strength of steel. Familiar with that? For different types of steel having different strengths. Okay, so we have different values for FY. LB is the unsupported or unbraced length. I will have to read the problem to notice or to take note of the phrases that would indicate the unbraced or unsupported length of our beam. And RT is the radius of gyration of the compression flange plus 1/3 of the compression web area about the y-axis. And later on, we will see the formula that we could apply in solving for this particular radius of gyration. Now, let's now proceed with our procedure. Okay, so this is our procedure. So take note of the steps that are involved and how we go about this particular formulas that we have. So number one, we check if the section is compact or non-compact. For the flanges, it's BF over 2TF less than equal to 170 over square root of FY for compact sections. Otherwise, it is non-compact. Okay, so we take note of this limit. For webs, we consider D over TW less than equal to 1680 over square root of FY for compact sections. Otherwise, the section is non-compact. Okay, so first we check if the section is compact or non-compact. Number two, second step, we check if the section has adequate lateral support. We determine LB from the problem. We will look for a phrase that describes the location of lateral supports or if it is laterally supported throughout. All right? And we have LC. We're going to compare LB with LC, where LC is the minimum of 200 BF over square root of FY and 137,900 over DFY over BF TF. Okay, let's proceed at the next steps. Let's have a look at the next steps. So once we have LB and LC, what we're going to do is to determine the relationship between the two. If LB is less than LC and the section is compact, then the allowable bending stress is equal to 0.66 of Fy. If LB is less than LC and the section is non-compact because of the flange, then FB is equal to Fy times 0.79 minus 0.000762 BF over 2TF square root of Fy. Okay? If LB is less than our LC, what do? Then the section is non-compact because of the web. FB is equal to 0.6 of Fy. So we take note of these comparisons and we decide on the applicable allowable bending stress. Okay? All right. Now, what about if LB is greater than LC? So this is what we consider in our next slide. Here on our next slide, we have LB greater than LC. Now, if this happens, regardless of shape classification, whether we have compact, non-compact, or slender, this is our procedure. So take note of this procedure. We're going to compute for this limit, and of course the middle value, which is LB over RT. All right. So LB is the unbraced length. RT, we have a formula for this later on. Okay. So we determine this square root of 703,270 CB over FY, and the other limit, which is square root of 3516,330 CB over FY. Okay. If our LB over RT falls under this condition, we use the larger of FB1 and FB3, but not greater than 0.6 of FO. Now, what is FB1 and FB3? These are the formulas. FB1 is 2/3 minus FY LB over RT squared over 10.55 times 10 to the 6 CB times FY. FB3 is 82740 CB over LBD over BF TF. Later on, we'll also have a look at the formula for CP, which is the moment gradient multiplier. Okay? Now, what happens if LB is greater than RT? LB over RT is greater than square root of 3516,330 CB over FY. Well, what we're going to do is we use the larger of FB2 and FB3, but not greater than 0.6 of FY. We must always take note of this. So we solve for FB2, 117,100 CB over LB over RT squared, and FB3, which is the same FB3 that we had in the previous slide here. Okay, so it's 82740 CB over LBD over BF TF. All right. So in this case, we have covered those particular criteria. What about if our LB over RT does not match these conditions that we have? So according to the code, for any other value of LB over RT, we are going to use FB3, but not greater than 0.6 of FY. What is FB3? FB3 is 82740 CB over LBD over BF TF. So this is the same formula that was used for the previous two slides that we have. Now you're probably wondering, what about that CB? Well, CB is a moment gradient multiplier. The code specifies the use of this formula to determine CB. So its formula is 1.75 plus 1.05 M1 over M2 plus 0.3 M1 over M2 squared less than equal to 2.3. What is M1 and what is M2? Well, M1 is the smaller end moment and M2 is the larger end moment. So it depends on your beam and what are the end moments for your specific LB. Okay? M1 is the smaller end moment and M2 is the larger end moment for the unbraced length that you are considering. If your unbraced length is the entire span or the entire beam, then it would be the end moments of the beam. If your LB is only a portion of the beam, then you have to determine the end moments for that specific segment or portion of the beam that we consider our LB. CB is equal to 1 for an LB with maximum moment within the span and greater than M1 and M2. Alright? So if there is maximum moment within the span, anywhere within the span, and it's greater than the end moments, and automatically CB is equal to 1. For cantilever beams, this is an exemption, and we also consider CB is equal to 1. Alright. Now, maybe you may be wondering, what is RT? What's the formula for RT? Well, this is our formula. RT is equal to the square root of IT over AT. IT over AT. So this is moment of inertia over the area of the T section. Why is it a T section? Because according to our NSCP, the T section that we're going to consider here is actually looks like a T. We have the compression flange plus 1/3 of our compression web area. Okay, so how do we solve this one? We have the following steps. First, we're going to determine this 1/3 of the compression web element. And this is equal to D minus 2TF over 6. As what we can probably say, 1/3 of the entire compression web element is actually 1/3 of the 1/2. And that is why we have 6 in the denominator. This compression web is 1/2 of the total web. So 1/3 of the compression. So 1/3 of 1/2 makes 1/6 the total clear web height. So D minus 2TF over 6. And IT is actually moment of inertia with respect to the y-axis. As per definition from the code, we have to take it with respect to the y-axis. That is why the formula here is TFBF cube minus XTW cube over 12. The area is simply the area of this shaded region that we have. Now, once we have IT and AT, we just apply the formula and that will now give us our RT, which we will use in the formulas that we have for the allowable bending stress. So this is everything that we need to know, our prerequisites, before we go over some problems and apply the formulas that we have and determine the allowable bending stresses for flexural members. I hope you enjoyed this video and please also watch the succeeding video so that you will also learn on how we apply the formulas that we have for today. All right.